kx. Déjà, c'est bon, ça marche. Ça marche pas. Si, ça marche. Ouais. Regarde le post. Là.
Oui, c'est aussi. Vont être arrêtés ce matin.
Bon.
Commencer, je pense.
Ouais. Et hello everybody. So Felix, you can start.
We can start? Okay. Yeah, okay. Good morning, everyone. Good to be back. Yeah, so let me just send this up, pasted the link, the Dropbox link again into the chat with the updated notes for today. Okay, so this is what I will try to cover today here. Yeah, so we'll complete sort of an outline of the existence by elliptic regularization. That's the first part. We already started with this on Tuesday. Then the next part will be the monotonicity formula, now sort of checking that this also works for Brakke flows. Yeah. Then we'll define what the entropy is and use the monotonicity of the entropy to show that this implies bounds on area ratio control, and then use this to show that it also in this weak setting here, we can always produce tangent flows. Yeah. So even in a weak sense, we always get these self-similar solutions which give first order expansions at a singularity. And what we'll see here, that these tangent flows in general, they will be just varifolds which solve in a weak sense the Schrinker equation. Yeah. So, but this still is often enough to get a lot of information about singularities. Yeah. So the Schrinker models can be singular by themselves, but they still carry a structure, which is then helpful in many cases. And again, as usual, please don't hesitate to interrupt me. Yeah? Okay, now here we started with elliptic regularization. Huh? Let's recall what was the setup. So this is our initial compact hypersurface sitting in Rn+1. And for this elliptic regularization, we put Rn+1 into Rn+1 cross 0 inside Rn+1 cross R, so Rn+2, yeah, where this additional artificial R direction has unit sort of coordinate vector E, yeah, and the coordinate we call Z, yeah. And then the idea was we minimize this e to the lambda z functional subject to the boundary lambda here. For that, we have to work with currents. So sigma can't have boundary and should be orientable. Yeah. So to do that, it works always in codimension 1. And then we can find these minimizers, which are critical points then of this functional. Yeah. And then the idea is that critical points of this functional exactly give us, here by translating them downwards here with speed lambda, gives us a family of translating solutions to mean curvature flow. So this is the setup here. Yeah. Let me draw a little picture here. Yeah. So just to remind everyone, so this is our coordinate system here. Here's this additional z coordinate. Here is our n+1. Here we had our initial surface here. This is sigma. Then we got these, they can go in and out maybe. Yeah. So this is our m lambda. And then m lambda t is exactly sort of that we start translating these downwards here. Yeah. They will have a boundary. Yeah. So they have this boundary here, but we'll see, we will later only work on this upper half space. So for positive times, yeah, the boundary is not there, it's just translated away. Yeah? The boundary of these translators is always in the lower half plane, and we're not interested in the lower half plane. Yeah? That's the idea. Okay, so this is why we do not have to care about this boundary there. Okay. Now, what have we shown here? So this is the important part. We have shown last time that if you look at the area of m lambda inside a slab between heights a and b, yeah, so this is here, such a sort of, here's b, here's a, could be kind of something like this here, that this area is always uniformly controlled here exactly by lambda inverse plus b minus a times the area of sigma. So here's the n-dimensional area, and this is the n+1 dimensional area. Yeah? So this, but what does this imply? Huh? This just implies that actually for these flows, these flows here, they have uniform area bounds. Okay. Now, what can we do now? So we can thus, by compactness, choose a sequence lambda I going to infinity, such that if we look at the following flows, yeah, T mapped, let's write it as really as measures, Hn+1 restricted to m lambda t, yeah, and let's call these mu lambda t. Yeah. This converges as lambda I goes to infinity to a Brakke flow. Again, defined for all positive times. Let's call this one mu t. Yeah. Now we just say we work just here in Rn+1 cross R plus. We just take the upper half space, so we don't need to care that these translators before had boundary. So what do we want to show? So what are the two important things today? First, is the first point is to show that the flow is translation invariant. I.e., we have that mu t is equal to sigma t cross R plus for sigma t a Brakke flow on Rn+1. Okay, that's already great. Huh? And then B, that this flow which you get, it has initial condition sigma cross R plus. Okay, and if you've done this, then really we have constructed a Brakke flow starting from the surface we wanted to start with. Okay. Now for translation invariance, yeah. So, and that's the sort of the way one should think about. Yeah, you see, you think actually of as the limiting Brakke flow as a Brakke flow where you have these cylinders, yeah, looking like this here. And in that sense, these translating solutions are kind of a more or less smooth flow approximating this weak flow in that sense. Yeah. Okay, so here's the translation invariance. Okay, so let's choose a test function in, I guess we need C2C actually, n plus 1 cross R plus. We let now here, okay, so it's like phi tau of x and z. X is the coordinate in Rn plus 1, z is the coordinate in this x dimension, yeah. And we just take this, we say phi of x, z minus tau. Okay. So we have shifted the test function upwards. Okay. Now, so recall, what do we have? This is the assumption, mu lambda I t greater or equal to 0. We know that this converges to this flow mu t. We know this is a Brakke flow again. Now, here's an important little note, but this is more or less the crucial point for this. If you look at m lambda t of phi tau, you see this is the test function translated upwards. This is the same thing as taking sort of translating, since this is a translating flow, to take that flow sort of when it has translated down by tau. But remember, speed is 1 over lambda, or speed is lambda, so the time is tau over lambda to be at the right height of phi. Yeah? Okay, everyone happy with this? You just wait the right amount for the translating solution to go downwards, that this is the same thing as first shifting the test function upwards. Okay, so this is really using the translation invariance of the approximation solutions. Yeah. Now recall, what do we know? Recall there exists a constant c phi, yeah, which is independent of lambda. Remember, that does not depend sort of just dependent on the area bounds, yeah, such that t maps to mu lambda t of phi minus c phi of t is decreasing in time. Remember, that was the crucial thing that we already also used for the compactness. So hence, for t less than s, we take lambda large enough such that we have t is less than t plus tau divided by lambda, that this is less than s, then we have following monotonicity, just using, it's just this monotonicity here now written down, written out, we have mu lambda t of phi minus c phi t, that's greater or equal mu lambda t plus tau over lambda of phi minus c phi of t plus tau over lambda is greater or equal than mu lambda of s of phi minus c phi times s. Okay, but see here now, this term we can just write here, actually using this identity up there, we can just write this as mu lambda of t of phi tau. Okay. Now, but what does this mean? We could letting lambda I going to infinity, This implies, what do we get? We get mu t of phi, this is just the convergence, minus c phi t is greater or equal to mu t of phi tau minus c phi t is greater or equal to mu s of phi minus c phi times s. I'm just taking the limit. And now, so if you take now s goes from above to t, then we get that mu t of phi is greater or equal than mu t of phi tau is greater or equal than mu t of phi for all t. Okay. Now, sorry, it's t plus here. Yeah. But recall we had proven initially that now we can extend this here. Now we assumed that this was a C2 test function. Now this last inequality allows us to extend this to just C0 test functions. And remember, we had shown that a Brakke flow has to be continuous for almost every time, or can only be discontinuous at all but countably many times. Yeah? So moreover, yeah, we had shown this initially. This was one of these first lemmas. Yeah. Moreover, we're using density. For all but countably many t. We have that t mapped to mu t is continuous at t. And so we get that mu t is equal to sigma t cross r plus for all but countably many t. Okay, and then what we can then just do, we can just fill in the missing times by limits from the left and right. Yeah, we can change the limiting Brakke flow up to uncountably many times. Yeah, then fill in the blanks by limits from above and below, or below. Yeah? Okay, so this gives translation invariance. That's great. So that's the first thing. You see the translation against this again using, so the crucial point is to use this monotonicity together with knowing that the solutions before are translating solutions. Yeah? Now, what is about the initial condition? Maybe before I do this, are there any questions regarding this? Okay. Please don't hesitate to interrupt me. Yeah? So, what is initial condition? We want to prove that mu0 is just mu of sigma cross r plus. Yeah? That's what we want to prove. What is the corresponding how, or if I write this differently, it's is hn plus 1 restricted to sigma cross r plus. Okay, so let's do, I have to recall a little bit something from which I didn't introduce, but I hope that most of you have heard this. Yeah? The flat norm, at least I'll give a quick explanation. Yeah? Script f, yeah? For A and B m-dimensional cycles. So what are cycles? It's more or less a generalization of m-dimensional surfaces or submanifolds S such that they have no boundary. Okay. Then the flat norm f of A minus B. So this is with orientation here. That's important. That's why we can say minus B is the infimum of the area of m plus 1 chains spanning A minus B. Okay. That's the flat norm here. Okay, now let's do the following thing. Let pi sub B be the projection on Rn cross B. Yeah, okay. And let, as read before, A lambda is pi b of m lambda 0b. I'll draw a picture in a moment. Yeah. Then what do we have? Yeah. The area of A lambda by the area formula, we can estimate this by m lambda times E perp. Yeah. See, if E is tangential, then the projection is 0. Yeah, that's exactly what we expect. Yeah, and we can estimate this here from above by just using Hölder, m lambda of 0b, m lambda of 0b. Now we can get a square in here. Times area Now we have shown this is always bounded by a constant, yeah. So the whole thing here, but this year we did estimate, this was one of our fundamental estimates from last time. So this is less than lambda inverse times area of sigma to the 1/2 times C, and this goes to 0. So this is the picture here, yeah. So you just look at this from the side, yeah. So here is Rn plus 1. Here is the C direction, yeah. So our surface, which color did I use here? Green, yeah, okay. So this is our surface sigma here. These two dots, yeah, just looking at it from the side, yeah. Then m lambda was now something like this. It's m lambda. Okay, now here is our height b. Okay, so the projection here is exactly where we take this part here down here, that part here, and project it here onto here. Yeah. Okay, so this is A lambda. Okay. Okay. So now what do we get from this? That the area, remember we're counting this projection with orientation, yeah. We have that the area in the blue region, this was what I shaded here, the blue region goes to 0. So what do we get? We get that the f, the flat norm of m lambda 0b plus A lambda minus sigma cross 0b, that this goes to 0. Okay. Yeah. So exactly, this bit here, yeah, this will go to 0. Okay. Okay. So this whole bit here, that area will go to 0. Now here's a general proposition from GMT. I won't prove it here now. So assume, but this we will use this, yeah. If we know that, you can, for example, read this up in Leon Simon's lecture notes. If we have convergence in flat norm, yeah, i.e. Ti converges to T as currents in flat norm, then what does one know? Then one knows that the mass, or the measure of T is, we have lower semi-continuity. Okay. Ti, can for example find this in Leon's book. So this is lower semi-continuity of mass under flat convergence. But even more, yeah, what you can actually show, this is even local. You can even show that the associated mass measures, yeah, that they're locally lower semi-continuous. Yeah, so this means in this process up here, yeah, it can't happen that at some point mass jumps up and at some other point mass jumps down to compensate. So you always have to locally, you can more or less only have local cancellations. Yeah, so you can't have, so you have this here, yeah. But with this we're actually finished, yeah. So this implies that if the total mass converges, then the measures have to converge. Okay. Now, what we had seen already, we have seen already that the measure of mu lambda, that this actually converges to the measure of mu sigma 0 cross r plus, the total measure. Okay, remember? Well, that was one of the estimates, yeah? That the measure of mu lambda on any, that really goes to the measure of sigma 0 across the interval locally. And if you look at these slabs, yeah? Okay, so this means the measures converge, but we have flat convergence as well. Yeah? So we get really convergence as measures, yeah? And this means that mu lambda 0 really converges to mu 0. Okay. And that gives that the initial condition is attained. Are there any questions regarding this so far? No? So we use our estimate from the beginning to argue that the total masses have to converge. Then with the estimate from before, we know we have convergence in flat norm, yeah? But then this implies that really the measures have to converge. Okay, and that gives that the initial condition is attained. Okay, now let's go to the monotonicity formula. Okay, now here just a natural definition, yeah? We say a measure mu 0 has bounded n-dimensional area ratios if we have the following inequality. If we take the supremum over all possible centers in our n+1 and all radii of mu 0 of br of x divided by omega n r to the n, this is just the measure of the unit Euclidean ball, is less than d is less than infinity. Yeah? So these are bounded n-dimensional area ratios. Let's call this one star. You need it a few times today. Okay, here's a little lemma. Assume mu t t very 0 is an n-dimensional integral Brakke flow on Rn+1 satisfying star. Then for t in 0 r squared over 4n, we have that the supremum over x in Rn+1 of mu t of br of x is less than 2 to the n+2 times d times r to the n. Let's call this star star. And what is the proof here? It's just this very initial monotonicity we had. Yeah. So this follows from the monotonicity of t maps to integral r squared minus x squared minus 2nt to the power 4 plus d mu t, yeah? As discussed before. Okay. But you see, this estimate is sort of okay, but you see, if you want to get with time very far ahead into the future, you have to make the radius big. You have to use big radii. That's the problem, no? Okay. Now, what do? We define now the backwards heat kernel. Most of you will have seen this for mean curvature flow. Define the backwards and we send it at a space-time point. In Rn plus 1 plus r. And so we say rho capital X0 at xt is 4 pi t0 minus t to the power minus n over 2 e to the minus x minus x0 squared over 4 t0 minus t. Okay, yeah, this is the ambient backwards heat kernel, where we change the scaling in t here a little bit in front and adjust it to the dimension of the surface. If it would be really the ambient backwards heat kernel, this would be power n plus 1 over 2. Okay, now here's the monotonicity formula. So this is the monotonicity formula. Which is in the smooth case due to Hüsken, yeah, and later sort of Illmann and White checked that the proof extends also to Brakke flows. So here's the statement: let mu t greater than 0 be an integral n-dimensional. Now here the dimension is important because we have to adjust the backwards heat kernel accordingly. Brakke flow in Rn plus 1. It works again in any codimension, satisfying star. So we want to have an initial control on the area ratios. Then for all 0 less than T1, strictly less than T2, strictly less than T0. We have the following inequality here: integral over rho x0 at T2, d mu T2, plus integral from T1 to T2, integral over mean curvature vector plus x minus x0 perp divided by 2 T0 minus T, norm squared, rho x0, T, d mu T dt, but this is less or equal to integral rho x0, T1, d mu T1. See, this is just the integrated classical monotonicity formula for mean curvature flow. Okay, let's prove this and see if we can get this. So here's a proof. Okay, but by translation invariance, we can assume that x0 is 0. We just shift x0 to the origin. Let rho is rho of 0 T0. Okay. So this is the heat kernel we're looking up. What do we know by definition? Remember, we have for any test function T2, d mu T2 minus is less or equal integral from T1 to T2. mean curvature squared plus mean curvature scalar product with grad phi plus d phi by dt, d mu t dt. Okay, for phi, what we needed here was C1c. Well, important, we need compact support. So it's important. We need compact support. Now, whenever the inner integral on the right-hand side is finite, i.e. when is this finite, i.e. mu t comes from an n-dimensional integral varifold with first variation in L2 log of mu t. Okay, that was the assumption, yeah. So we have a, so for almost, we know for almost every time here, this makes sense here on the right-hand side, yeah. So we have a varifold, and we can integrate, yeah. These times we can now compute, yeah. We have by the first variation formula now see, so if you integrate, have integral over h squared times phi plus h grad phi plus d phi by dt, d mu t. We can rewrite this a little bit. We just add something like minus mean curvature squared times phi. Now we want to get a factor of 2 here, h dot grad phi, but we have made a mistake, and we can correct for this mistake by saying, okay, divergence over the tangent space of grad phi. See, this exactly cancels. One of this cancels this factor 2 here, plus d phi by dt, d mu t. Okay. Now see, but you see, this allows now here to start completing a square. Now we can write this here as minus phi times mean curvature vector minus grad perp phi over phi, norm squared, plus q. Now here there's a vector v, I'll define this in a moment, v mu t of phi d mu t, where how's this qt defined of phi is just gradient perp phi norm squared divided by phi, plus divergence, tangential divergence of in this tangent space with respect to phi, plus d phi by dt, for any n-dimensional subspace T of Rn plus 1. Okay, so if you look at this here, and see if you know the square, you get this, the first term is this, then the cross term would be this, and now this term here, which is in here, gives you exactly compensates with that term here. Okay, so this gives a plus, this 1 squared minus phi gives you exactly, cancels 1 in the denominator, that gives this term. Now this term goes in this term, and this term goes also in there. Okay, and now here's the important thing, the magic, note qt of rho, actually if you put the backwards heat kernel in, that's always 0, independent of the subspace. Yeah. Okay, but we can't really insert rho yet because rho has not compact support, but at least this is vanishing pointwise there. Yeah. Okay, now we have to argue that we somehow want to be able to, instead of having here a test function, we want to insert rho. Yeah? Okay, so what the usual thing is, we do a cutoff, yeah, to insert rho into the above formula. Okay, we just take a cutoff function, psi is psi r, yeah, be a cutoff function. Such that we want to have that it is 1 on the ball of radius r around the origin, and it is 0 outside the ball of radius 2r. Okay, and we want to have that r times grad psi plus r squared times the Hessian of psi is less than some constancy. Okay, it's just a normal cutoff function. Just take it radial if you want to. Now you calculate, and it's also a little exercise. I also carefully did this. Yeah, you can get the following formula. If you take qt of psi times rho, yeah, then you can write this as psi times qt of rho plus rho qt of psi plus 2 grad psi grad rho. Okay, now we know this term here vanishes, because this is vanishing. And you can estimate this from above by c times 1 over r squared plus 1 over t0 minus t times the characteristic function of b2r of 0 without br of 0 times rho. So this is a little exercise. Just a direct estimate, where we have used. So what is the important estimate that we can estimate grad rho from above by rho times modulus of x divided by 2 t0 minus t. Okay, so that's the trick here. Yeah? See, this comes when you want to estimate that term here. See, so you get here 1 over r factor that kills the x factor, and then you can have the t0 minus t. Okay, now, so if we inserting psi times rho above, we get, what do we get? We get that integral over psi times rho d mu t2 plus integral from t1 to t2, integral over psi mean curvature vector plus now we have x perp, that's what we want, over 2 t0 minus t. That's good. Now we get an additional term which is grad perp psi over psi squared rho d mu t dt. Okay, and is lesser equal than psi times rho d mu t2 plus c over r squared plus c times t0 minus t2 and integral from t1 to t2 b2r of 0 without br of 0 over rho d mu t dt. Okay, now, so you see this is good here, because you see here we can use the, if you let's send now r to infinity, this term will go to 0, because we have so you note by star star that we have that the supremum where t lies between t1 and t2 of rho d mu t is less than infinity. Remember, we're staying away from the concentration time. And if you look at this term here, the other term you have to think about is this term here. But you look here, you get a cross term here, but the cross term is okay because we have this other factor of psi. Then we get a term where this term is squared, but you see that term also is okay because we get something in the end which is grad psi squared divided by psi if you multiply in here. And remember, that's bounded by second derivatives of psi. Yeah? But we see the support of that function sort of is in an annulus which goes out to infinity, and we're integrating against this rho, which is exponentially decaying. Yeah? So that term will vanish in the limit. Okay, and then the result follows by the monotone dominated convergence theorem. Okay. So this means we have really also just the normal monotonicity formula for Brakke flows. The idea is you kind of use this bound on the area ratios to make sure that the exponential decay here of the rho wins at infinity. So you could even assume sort of worse area growth. This would still work. It's just this exponential decay of the rho has to be good enough to counterbalance that. Are there any questions regarding this so far? Okay. No. So this means we have the monotonicity formula. Yeah? Okay, now let's discuss entropy. Now, for a surface, +1, we define just the weighted area measure. We define f of m is just 1 over 4 pi n over 2 m e to the minus x squared over 4 dhn. Yeah, it's more or less, you see, up to scaling, this is what appears in the monotonicity formula. Yeah? Or more general, for a radon measure, or more generally, for a radon measure mu, we will need it for measures as well. Yeah, we set fn of here. Now this doesn't have a dimension. Yeah, so we have to put the dimension in the definition. Yeah, 1 over 4 pi to the power n over 2 integral over e to the minus x squared over 4 d mu. Okay, which is finite if we, for example, assume that these measures have bounded n-dimensional area ratios, even some kind of control at infinity. Now let a of r be just mu of b0r. Note a of r is increasing in r. Sure, it's just monotonicity. And thus, then you know, but for an increasing function, you know that the derivative exists as a radon measure always. And thus a prime of r exists as a radon measure on r plus. See, if you have a monotone function, it can have countably many jump times. At these jump times, you get delta measures, and otherwise you get the derivative. Okay, then, but this means we can integrate by part. We can first use core area and then integrate by parts. Then we have by integration by parts, assuming a of r grows sub-exponentially. Also always can assume this in what we're doing here, that we can write fn of mu as this is core area, just in the setup. We can write it as 0 to infinity, e to the minus r squared over 4, a prime of r dr. This is core area, because a prime of r always gives us more or less the measure that lies on every shell at radius r. Now here this is 1 over 4 pi n over 2. Now we can integrate by parts. So if you integrate by parts here, this gives omega n over 2, r to the n plus 2, and we can write this as e to the minus r squared over 4, and we write this here as a of r divided by omega n r to the n dr. And I'm writing this in this way because this exactly are the area ratios. Okay, now we can use this description here. We know a prime of r is always positive, yeah? So we can bound this from below. Yeah? We can also estimate for any r0 positive, yeah, that fn of mu is greater or equal to 1 over 4 pi n over 2, r0 to infinity. Now we're using this here, using this directly. Huh? So if you rewrite this, you just get here r over 2, e to the minus r squared over 4, a of r dr. Huh? Just sort of canceling these factors of r, which I put in artificially here. Yeah? And now this we can integrate by parts. This is, we can write this here as minus 1 over 4 pi to the power n over 2, r0 to infinity, a of r, d by dr, of e to the minus r squared over 4, dr, huh? And you can check that is greater or equal to 1 over 4 pi to the power n over 2, a of r0, e to the minus r0 squared over 4. Okay, just by use that that's one of the boundary terms. Okay, so what do we get from this? So there we get the following estimate. You see, this estimate gives us the following upper bound, yeah, omega n r to the n divided by 4 pi to the n over 2, e to the minus r squared over 4, a of r divided by omega n r to the n. Yeah, see, these are the area ratios, is bounded from above by fn of mu. But we have seen we can control fn of mu if we control the area ratios. So this is this formula up here. Yeah? See, if we control the area ratios, we control fn of mu. So this is controlled from above by the supremum of r greater or equal than, let's say, 1. Yeah? A of r omega n r to the n. Okay. So this gives us a nice control here. This tells you, okay, we can control from below and above, and you see, okay, this factor deteriorates if r goes to infinity or r to 0, but at least if r is sort of bounded away from 0 infinity, this gives uniform control. Yeah? Now what Kolding and Minicozzi have introduced, and this is sort of similar to Perelman's mu entropy, yeah? To find a related quantity called entropy as lambda of m for a hypersurface is just the supremum over all lambda positive and all centers p in Rn plus 1 of f of lambda m plus p. Yeah? So you scale and change centers. Yeah? And where we define lambda n of mu correspondingly. Okay, what do we know? But you see, this now we're changing here now any scale and any center. So this means we can more or less always assume r is 1 here. But if we want to bound just by the supremum, we see we can first we get a control by the error ratios from above always, because we're taking a supremum here anyway. But since we're taking any scale here, we can take r equal to 1 to control all area ratios. Okay, so by the above bounds, we see that there exists a constant c is just depending on the dimension, such that for, if we take a of pr is mu of b, p, and r, then we have that the c inverse times the supremum over all p in Rn plus 1 and r positive of a, p, and r divided by omega n r to the n is less than lambda n of mu, and that is controlled again also by the area ratios, the supremum over p in Rn plus 1, r positive, a of pr, omega n r to the n. Okay. Now, what you see here, for a fixed lambda and a fixed center p, we see that we can just use the monotonicity formula and get monotonicity in time here of this quantity here, by just changing scale and choosing this correspondingly. So as similar as Perelman, so here's the corollary. Let mu t greater equal be an integral Brakke flow n plus 1 with bounded area ratios, so it has bounded entropy, then the entropy lambda n of mu t, that's why we needed it for radon measures, is finite and decreasing with respect to t. Okay, furthermore, the area ratios are uniformly controlled for all time. Okay, so this is one of these, this is like non-collapsing for Ricci flow. So you see here, the trick is here now, so the monotonicity formula really gives you control on the area ratios on all scales for all times. So you always have uniform control. Whereas before, from this first lemma we had here, this very first initial one, this one here, that only gave some control, sort of on a certain size, but not for very small balls for very light times, uniform control. Okay, so this gives uniform control for all times. Okay, now what does this mean? Now we can look at tangent flows. Okay, before we continue, is there any question? Okay, now let's do tangent flows, and this is, I think, the last thing I'll do today. And we can discuss this a bit, Okay, now we first want to define what are parabolic rescalings, So denote the parabolically so first let mu t is in some interval be an integral Brakke flow. When we look at the parabolically rescaled measures around x0, which is just x0, t0, space-time point. Now, this is the same thing as just parabolic scaling in the smooth setting. Yeah. So we look at mu t of x0 with a positive factor lambda. Now we have to define it for measures. So we say what happens if you plug in a set A. Yeah? So we say this is the following thing. We take mu at t0 plus lambda to the minus 2t. Yeah? So we shift time t0 to time 1, and we scale time by a factor lambda squared. Now we scale space by a factor lambda. So this means we have to change the argument by lambda inverse. Yeah? We shift the origin to x0, and now we have to still, since these are measures, we have to scale here the measure by lambda to the n. Okay. Now, so you can check here that the interval of definition is now this interval I. You shift by t0, yeah, and so here is t is in here, yeah, and you scale up by factors t squared, yeah. Then you map this to mu x0 lambda t. That is again an n-dimensional integral Brakke flow. On our n+1. And you see the important thing is here, if this flow before has an entropy control, that flow still has the same entropy control because it's just we shift by scaling and by translation, and that already we took out in the definition of the entropy. Yeah, so this is the note here. Yeah. Note, if the initial flow has entropy bounded by C, then so does mu t x0 lambda. Okay, so this is just a parabolic rescaling of this flow. Okay, and now here is the existence of tangent flows. Yeah? Okay. And again, the idea why this is so strong in the end, this works without any regularity assumption. You can always look at tangent flows, and the tangent flows still have as a good structure as you can hope. Huh? And then you can sort of try to understand your solution by understanding what kind of tangent flows can appear. Yeah? Now, there's a similar take for minimal surfaces. When you can kind of classify or rule out certain tangent cones, then you know more about the regularity of your solution. Yeah? So for any sequence, lambda I going to infinity, there exists a subsequence. We can say labeled the same. And the Brakke flow T, and this is now defined for all of R, yeah, such that we have with these rescaled flows mu t x0 lambda I, they converge in the sense of convergence we got out of the compactness theorem to this flow nu t. This is defined for all time. And we know what we know is we know that the flow is self-similar, the limited flow for negative times. Nu t of A is the same as if you just scale the flow by a factor lambda, yeah, is the same as lambda to the n nu of lambda to the minus 2t lambda inverse of A for all t negative and for all lambda positive. Yeah, okay. If you look at this formula, you can just take lambda more or less is square root of minus t, yeah, and then you see you can write nu t of A is just the right scaling of nu minus 1. Yeah? So this is exactly self-similarity. And what do we also get? That nu minus 1 satisfies an elliptic equation, satisfies the Schrinker equation, plus x perp over 2 nu minus 1 almost every x. And you see this makes sense. So this is implying that nu minus 1 is actually a varifold, and that equation makes sense for a varifold. So this means nu minus 1 is a varifold with prescribed mean curvature, where mean curvature is exactly prescribed by x perp. So that still makes sense for varifolds. And furthermore, what do we also get? We get, if you look at sort of this, at the Gaussian, this Gaussian integral at any time t over nu t, for t negative, this is constant in time, and we can compute it as the limit of t prime going up to t0 of rho of the original flow rho x0 d mu t prime for all t negative. If you think of this, this is, I didn't define this. This is the Gaussian density here. So this means the Gaussian density of the original flow is exactly the Gaussian integral, the Gaussian area ratios of the limit flow. Okay, let's prove this. We just to make things a bit easier to write, we write mu lambda t for mu t x0 lambda, and rho of 0, 0, you write as rho, okay? Okay, so we shift x0 to 0, the flows, again, mu lambda t have bounded area ratios. Again, that's what I was stressing before, since this is the natural assumption by the previous discussion. So we can apply the compactness theorem. By compactness, there exists a subsequence. We label this again. Call this lambda I going to infinity, such that mu lambda I t converges to some flow nu t, where this is defined for all t in R. Remember, our initial flow was defined for all positive times. We took a positive time, and we shifted then, so we scale up. So this is now defined for all R. Now we know that the limit flows also have bounded area ratios, since the flows have uniformly bounded area ratios. For every, if you fix a negative time, for every t, so our Gaussian heat kernel is not completely concentrated, and epsilon positive, there exists an R positive, such that we have that the supremum over I of Rn plus 1 without BR of 0 of rho d mu lambda I t, that this is less than epsilon, because we just use the exponential decay of the heat kernel, and we stay with t away from 0. Now we can just use a cutoff function, using a suitable cutoff function, and we have reconvergence mu lambda I t going to nu t. We have that the limit d nu t, that this is the limit as I goes to infinity, d mu lambda I t. But remember, this we can rescale the whole thing. That scales in the right way, and you can check. This corresponds to an initial sequence of times going to times t0, but there we can use the monotonicity formula. This is the same as going with t prime going to t0, where rho x0 d mu t prime for t negative. So this is a little exercise here. Yeah? You can check this. So this gives you, so this transforms in the right. So here's the exercise. Yeah? So if you check the scaling here, this really, these integrals are scaling invariant. Yeah? So you have to, you change the scaling here of this backwards heat kernel in the right way. This corresponds, these times lambda I going to infinity with a fixed time here corresponds to a sequence of times ti going to t0. Yeah? But since this is a monotone quantity, we know this does not, we just have one sequence, so this does not depend on which sequence I take. Yeah. But that also means this here, that term here does not depend, this is independent of the time t here, yeah? Which already gives that this is constant in time here. Okay. Where the last equality follows from the monotonicity formula. Okay. Now, this means this limit flow here, the limiting flow has this here constant in time. Yeah? So it does not depend on time. Yeah? But then, again, by the monotonicity formula, for nu t centered at 0, 0, yields that for almost every negative t, we have that, you know, this means that it's constant in time along the monotonicity formula. So we know that nu t is an integral, is an n-dimensional integral varifold with mean curvature in L2 log of mu t, and it satisfies mean curvature vector plus x perp over 2t is equal to 0, nu t almost everywhere in x. Okay, that is great. But we don't have it for time -1 yet. Now we have to now show that it's self-similar in time. No? That's really self-similar. No? Okay, so to show self-similarity, now we do it the other way around. We define, if it's kind of want to take out the scaling, we define nu t of a, nu twiddle of a is just minus t to the minus n over 2, nu t minus t over minus 1/2 a for t negative. See, this is exactly just taking out the standard normal parabolic scaling. So it suffices. So what you want to show is that this is constant in time. So it suffices to show that nu twiddle of t is constant in time. Now, if we have done this, then we're finished. Because if this is finished, then we know that this equation here holds for all t, and really we just get self-similarity. Okay, how do we do this? We take a test function in C2C again as usual, Rn plus 1, R plus. And now we want to put the scaling now on the test function. We take phi twiddle of x and t. We just define it by minus t to the n-half phi of minus t to the 1/2 x. So note the following quick computation, that d phi twiddle by dt is minus n over 2t phi twiddle minus 1 over 2t gradient of phi twiddle, scalar product with x, and can quickly compute this. Now, by definition, by the definition of Brakke flow, what do we get here? Yeah? So we have, what do you want to compute? We want to prove it's constant in time. Yeah. So d nu twiddle of t2 minus phi d nu twiddle of t1. Yeah. Now, okay, we can, the idea is exactly this is chosen that this is the same thing as looking at phi twiddle d nu t2 minus integral over phi twiddle d nu t1. You can check this. Huh? Now, but for this here, you see, for this here now, we can use just the definition of Brakke flow. This is less or equal than integral from t1 to t2. Now, minus n over 2t, phi twiddle. This is the time derivative. Minus phi twiddle mean curvature squared plus grad phi twiddle mean curvature and minus 1 over 2t grad phi twiddle times x d mu t dt. Okay, sorry, d nu t. D nu t dt. Okay, now we can rewrite this by knowing, but we still have the equation for almost every time, so we can put it in t1 to t2 integral minus n over 2t phi twiddle. Now we replace 1 h by x over 2t. So this gives this term h comma x. Now we can, in this term, you also replace h by x over 2t. So we get here gradient phi twiddle times x perp over 2t minus 1 over 2t. So we replace the h here, minus 1 over t, gradient phi twiddle x, okay, d nu t dt. And you see now what is nice, these two terms combine here. Yeah? And what do we get here? We get that this is equal to integral t1 to t2 minus n over 2t phi twiddle minus phi twiddle over 2t hx minus grad phi twiddle x tangential over 2t d nu t dt. Okay, so this is great. Yeah? But now, again, we use here integration by parts on this term. Yeah? So we have integral minus phi twiddle divided by 2t hx. This is the same as 1 over 2t, the divergence over d nu t phi twiddle x d nu t. And okay, but this we can compute here. Huh? So this just gives here, when the divergence falls on the x, this gives the dimension. This is n over 2t times phi twiddle, plus now we get here gradient of phi twiddle times x tangential, or tangential gradient, over 2t d nu t. But you see, these two terms cancel exactly these two terms. Yeah? So what does this imply? This implies that integral phi d nu twiddle of t is non-increasing in t. That's the first thing we get. Yeah? Since we have Brakke flow, yeah, we only get one direction. Yeah? Now what we can do now, there's a little trick in the end now to get identity. So assume, without, just by scaling, we can assume that our test function is scaled such as less than the heat kernel, than rho. and apply the same calculation to rho minus phi. Yeah. Now this is not, doesn't have compact support anymore, but it has exponential decay. Yeah. So we can use using exponential decay of rho plus bounded area ratios to validate the insertion of rho minus phi, yeah, to see that also integral of rho minus phi d nu t is also non-increasing in t. Okay, but you see, if this function is non-increasing, this function is non-increasing, remember we've proven that the integral over rho is constant in time. Yeah. Yeah, so this is the fixed rho. This is not rho depending on time. Yeah, this, we took the scaling out. Yeah, so this is constant in time. Yeah. Now, since integral of rho of d nu twiddle of t is constant in t, we get that integral over phi d nu twiddle t is constant in t. Okay, and that would be it. So that gives the full self-similarity of the limit. Yeah? So this was in the end a bit technical. But so this gives really sort of this nice result that you can always look at tangent flows. Yeah, you need bounded area ratios. Yeah, and then you can do blow-ups and look at tangent flows. Yeah, see, the important thing is this tangent flow might not be unique at a point. Yeah, if you have different sequences, you might see something different, but you can start using now tangent flows to understand sort of the singular set of a Brakke flow and more. Yeah? Okay, so this is what I wanted to cover today. Are there any questions?
So what kind of tangent flows, is there like any attempt to like classify tangent flows? I guess there is, but
yeah, there is. For example, like if you have mean convex mean curvature flow, even weak mean convex mean curvature flow, you can still prove that you can only get shrinking spheres and cylinders.
Yeah, I know that, but can singular objects appear as tangent?
Yes, yes, yes. So there can be, for example, be singular minimal cones. Yeah.
Okay.
This is sort of similar like for four-dimensional Ricci flow, where you then get Ricci flat cones appearing. Yeah. And you can do stratification. Yeah. Yeah? So you can start saying, okay, you can define, if you know stratification, you can define what is a spine. Yeah.
Yeah.
You have to count sort of spatial and time directions differently. And then if you can rule out certain tangent flows with enough symmetries, then sort of know that your singular set has to have certain parabolic codimension, host of codimension in the parabolic sense. So that turns out to be extremely helpful. Yeah? So that allows you to do this whole machinery, yeah, that you know from minimal surfaces.
Yeah, I understand. Yeah. Okay.
So very, very good. Yeah. So you can now really start to understand the singular set. Yeah. You can, for example, also prove so a regular point would be, for example, if the tangent flow is a unit multiplicity static M-plane. Yeah.
Yeah, that makes sense, of course.
Yeah, and then you can, then there's an Aller type theorem which says, okay, if you have that tangent flow, then actually your flow is regular around that point. Yeah.
Yeah. Also, can you have higher multiplicity? Like
yes, sure.
So it can happen, yeah.
Sure, yeah, of course. This is the big question, yeah.
Yeah.
Yeah. So these flows can have multiplicities. Yeah.
Sure. Yeah. Okay.
Simplest example is just a double density plane, which just sits there in time.
Yeah. Okay. Yeah.
Or you can just take a minimal surface. static minimal surface is a Brakke.
Yeah, for minimal surfaces, I know. Yeah.
Yeah, but the same thing happens here. Yeah.
Yeah. Okay. So it happens. You cannot avoid the multiplicities. It's
No.
just you don't have like a city theorem or anything like that.
No, it's much harder. Yeah. In the case, if you're mean convex, then you can rule out cheating. In some sense, you can treat mean convexity as some kind of stability, because of kind of then sort of this work of Brian White, and of mainly Brian White and other people then later shows that you can't get cheating in the mean convex case. You always have multiplicity 1.
Okay, that's interesting. Yeah. Thank you.
No questions from the room.
Okay.
Yeah.
Okay, if not, so then I'll see everyone again tomorrow. I'll put these notes in the Dropbox. And thank you all for your attention.
Thanks, Felix. See you tomorrow.
See you tomorrow.